Okay, so welcome back. In the first lesson on the monomial derivatives, we found that when you differentiated x cubed, you ended up with 3x squared. Now, just so we can make reference to the working out we did in this section over here, I'm going to bring out a new blank page so we can figure out how to find higher derivatives. To make the idea clear, let's start by imagining m4 of x plus change in x. So, since we're raising it to the power of 4, we have 4 brackets instead of 3 this time. First, let's expand the term where you only have x's. So in this case, it's x times x times x times x. And now, we'll look at all the different ways where we can have exactly one change in x. If we choose the first bracket to be change in x, then the other brackets have to just be x. Then we can also choose to take change in x from the second bracket, so we get x times change in x times x times x. Now we can also take change in x from the third bracket, so we'd get x times change in x times x. And then finally, we can take the change in x from the last bracket, so we'll get x times x times change in x. Now, we've actually covered every term we care about here. For absolutely any other term you pick, you're always going to have more than one change in x, and therefore we call these higher order terms. Now, as we can see, this means that x plus change in x to the power of 4 is the same thing as x to the 4 plus 4 groups of x cubed change in x. And then we have to remember to add on the higher order terms. So if we want to replace this 4 for an n, we first have to notice that the first term just comes out as x to the power of n. And now, to generalize this term, we actually have to notice that in each of these terms there are exactly 4 letters, corresponding to the 4 different brackets. Since we want exactly one of them to be a change in x, then all the others have to be x's. That means in the case where you have 4 brackets, you'll have exactly 3 x's in the final answer. And you have 4 different ways to choose change in x. So this 4 over here corresponds to the 4 different ways, and this 3 over here corresponds to the fact that we have 3 x's left. The 3 is always going to be 1 less than the 4. So in the case where we have n brackets, we're going to have n different possible ways to rewrite this. We're going to have one change in x. Then, for example, if we chose this one to be the change in x, then the remaining n minus 1 brackets have to be x's. And therefore you have n minus 1 x's. And then after this, you're left with only the higher order terms, which, as we said, we don't really care about. Now, this result over here is actually going to be really important. We're going to use it to repeat this calculation again, but we're not going to force n to equal 3. We're going to do it in general. So I've left this result over here because we are going to need it. Now, as we said, we'd like to differentiate x to the power of n, and to do this, we're going to have to use the first principles definition of the derivative. So here I've just written out the exact same thing we've written in the last case. We know that m of n is x to the power of n, so we can replace it over here. Now the first thing we're going to do is we're going to expand this by using this formula that we came up with earlier. Now when we do this, we notice that the first term and the last term just end up crossing out. And now we can just split the two fractions and cross off the change in x in the first term. Now we have a very familiar form to the one that we had before. So in the last step, we just take the limit as change in x goes to 0. And as we know, higher order terms just cancel out when change in x goes to 0. This is because all of them have more than one change in x in them, and when you divide by change in x, there are still some change in x's left over. And now we've actually reached a pretty important part in your mathematical journey. We started off with a simple definition about what we mean by a derivative. And then after doing a little bit of algebra to it, we end up with this formula over here. This formula actually allows us to find derivatives without ever needing to think about limits at all. This has actually led some people to call differentiating a technology, because you can kind of do it without really knowing how it works. Unfortunately, however, because you can do it without knowing how it works, a lot of courses on mathematics don't actually show you how it works, and I think that's a little bit of a crime. Now, I think it's time that I showed you how to use this formula. And I think you're going to be amazed by how much easier it is than having to do all of those weird limits that we had to do before. So let's pretend we wanted to differentiate x to the power of 37. Now, doing all of this would be absolutely insane, so we're not going to do it. But our rule over here says that if n is equal to 37, then we can just write its derivative as 37 x to the power of n minus 1, or 37 minus 1. Now, of course, 37 minus 1 is just 36, so we can write that instead. And just like that, our job is done. That's pretty cool if you ask me. A lot of people remember this rule as the bring the power down rule. That's because you actually bring the power down in front of the x and then subtract 1 from it. Now, I'd like to give you one more example, but before I do, let's actually run our little sanity checks. Now, for m0 of x, we know that m0 is the same thing as x to the power of 0. Following our rule over here, the derivative is just going to become this. So we brought the power down and then subtracted 1 from it. Now, 0 times anything is just 0, so we do indeed see that the derivative is just 0, as we expected. Now in this case over here, we can actually say that m1 is x to the power of 1, and if we differentiate it, we get this. Now we know that x to the power of 0 is the same thing as 1, so we can replace it. Now 1 times 1 is just 1, and as we expected, the derivative of x just ends up being 1. And so this formula over here is actually pretty cool. It can handle basically any power of n that you throw at it. But of course, there are some cases that we didn't actually consider here. We did this whole proof assuming that n was an integer. Now, what if n isn't an integer? Would our formula just break down and stop working? Well, actually no. Since the formula works for integers, we assume that it's going to keep working for non-integers. Proving this isn't so easy, but it is something that you can do. Of course, it's not going to be easy, because we have no idea how we would expand this if n was not an integer. Now, at the risk of spoiling this for you, I can tell you that you get the exact same formula when n is not an integer. But proving that is definitely not something you do in a first course on calculus. So we're just going to assume for now that this function works for any power of n. In fact, if I'm being really honest, the proof we did only really works when n is actually a positive integer. So just to give you a little bit more confidence in this formula, let me go ahead and actually pick a case where n is actually a negative number. Now, if we just blindly follow the bring the power down rule, we'd bring the power down and get minus 1 x to the power of minus 2. Now, x to the power of minus 1 is just the same thing as 1 on x, and minus 1 x to the minus 2 is just minus 1 on x squared. So to actually verify that this makes some sense, I'll go ahead and draw on this graph and this graph over here. So at least to me, this looks like it works quite well. Initially, the gradient's just a little bit negative, so we get a slightly negative value. And then the gradient gets more and more negative, so the value gets more and more negative as well. However, when we pass x equals 0, the gradient is still actually negative, and it's really negative, so you actually notice that it starts off really negative over here as well. Then, as we get further to the right, the gradient gets closer and closer to 0, so we get this value getting closer and closer to 0 as well. Now, this actually completes our example, and I do hope that this justification satisfies you at least a little bit. It is perfectly possible to prove this formula for any value of n, but this is something we'll tackle later on. And now I'd just like to summarize everything for you. We said that a monomial was just any function written in the form x to the power of n, and we've graphed a few of them over here. To find its derivative, we started by writing out the first principles formula, and then we expanded the brackets to get these higher order terms. After doing a little bit of algebra, we ended up with this formula over here, which we call the bring the power down rule. By using this formula, you never actually have to perform these tedious steps ever again. But, as we pointed out, this formula only really works when z is a positive integer, so we just kind of assume that it's going to work for any other value, which is something we'll have to prove later on. And with this, we've actually completed our discussion on the monomial derivatives.